Good evening from Bangladesh. My name is Harij Uddin. I am going to present a novel snake identification method, which is solely based on quantitative analysis of microdermatoglyphic features of shade of snake skin. Please give me some time. I am going to. Okay, it seems like okay now.
Yes, that looks great.
Thank you
It's
for
full
your
screen.
patience. Okay. Providing this of case for taxonomy, snake bite management, ecodiversity, conservation, diversity, and one. So all the existing methods of snake identification have some limitations. For instance, visual identification is highly unreliable due to close similarities of snake species. Morphometric identification is risky because it often needs live handling of snakes. And other issue is that finding out a snake is very challenging because it tends to blend in its environment. That's why it is very difficult to spot one. And the another issue is that anatomical identification often requires to kill snake specimen that is not good for biodiversity. Molecular identification, although highly accurate, it is time consuming, costly, highly technology dependent that limits its applicability in various resource constrained regions like underdeveloped or poorer countries. So it is crucial to develop a new method that can overcome the drawback of the existing methods. Snake periodically shed their skin and that can be found easily in the environment, which lasts for several weeks to months. And this shaded skin poses ultramicroscopic features which can be converted into metric data. And if this data can be analyzed and identified the snake that leave it behind, so it can be a traceable representative of the snake that left it behind. So when a snake shed its skin, it's preferentially seek out a secure microhabitat where it is mostly safe. So if we can identify a snake using its shade of skin, we will be able to infer its habitat utilization pattern and various aspects of its microhabitat. Considering the importance of snake identification, drawback of the existing methods, prospective implication of shade of skin, we conducted scientific approach to develop a new and novel taxonomic method to identify snake solely based on microdermatoglyphic features of the shade of snake skin. For this purpose, we choose two snake species that are very congeneric and those frequently shed their skin and causes snakebite mortality and morbidity in various regions of the world. So, at first, we choose 7 body regions of a snake skins that you can see in the slides: head, neck region, mid body, preanal, anal, post anal, and the last one is subcaudal. So from these 7 body regions, we selected 15 scales in such a way that these scales more or less represent the whole body of the snake. After collecting shade of skin, we initially prepared the skin by washing, manual cleaning, drying, and finally storing into zipper bag so that it can be remain in good condition for long period of time. After bringing it into laboratory, we prepared slide cutting various parts of the skin that you uh, saw in the earlier slides. And after cutting, washing, we transferred the section of skin into slide. After drying, we observed the microscopic features of the shade of snake skin at various magnifications and photograph parts of the snake skin. And after the photograph is taken, we analyze the data using software image focus alpha, and the data is transferred into the Excel sheet. So here in the first picture, picture A, you can see two regions of a snake skin. One is edge region and the other one is interstitial follicle regions. And in the insect B and C, you can see the structures that is present in these two regions. Those are in 400 magnification. And finally, here is the most interesting part, that we have been able to quantify 6 microdermatoglyphic characters that you can see in the uh, figure A. We have developed 3 characters: edge perimeter, edge area, and edge widest part distance. So how we measure these parameters? At first, we draw polygon around this structure. You can see in color here. I'm not sure whether my cursor is visible or not. Around these structures, and the software measures the perimeters and automatically the area covered within. And another line measures the widest part of this is structure. And in picture B and C, here and here, we measured another 3 microdermatoglyphic characters, that is follicle perimeter and follicle area. Like the previous one, here we also drawn polygon around the shape, and the software automatically counted the perimeter and the area within this polygon. And in here, picture C, we have drawn a rectangle of 20,000 micrometer square, and all the structures that fall within this rectangle were counted. And here is an issue that some structure fall inside part of it inside and part of it outside the rectangle. And to address this issue, we counted those structure that fall more than 50% inside the rectangle. And we have counted a lot of data. Actually, for each character, we took 30 repeated measurement, and our sample size was for 7 specimen per species. That is 7 specimen of NK, that is Naja Kaufia, and 7 specimen for Naja Naja. So in total, we had 14 snake specimens. That's why we have a bulk amount of data, 420 rows and 90 column. That is my data structure. And after generating this bulk data, we had at first performed Shapiro-Wilk test to check the normality of data distribution, then student t-test or Wilcoxon-Sandring test. If the data were normally distributed, we perform t-test, and when the data were not normally distributed, we perform Wilcoxon sign rank test. So why we perform this test? We perform this test to see two aspects. That is the stability of the character in between, within a specimen of a species and in between specimens of a species. And the another aspect was that whether these microdermatoglyphic characters differs in between the two snake species, the Naja naja and Naja kautia. And finally, we perform principal component analysis to investigate that whether these characters are capable of producing species-wise and sex-wise clustering. I forgot something that we also perform this test to investigate whether male and female uh, specimens of a species can be separated using these microdermatoglyphic characters. So here you can see the first aspect of our analysis in figure A, that is Naja kautia. Each area was the highest stable character, and in both cases, and also the least stable character showed more than 50% stability in both species. So we can, uh, and here you can see the comparison in between specimens where is widest part distance showed highest stability in Naja kautia, and other characters also showed considerable stability in various scales. And also here for Naja naja, is widest part distance showed the highest stability, and other characters also showed considerable uh, stability in various scales. Here in this table, we can see the result while we compare in between Naja naja and Naja kautia. So the total comparison were 15 for each character. You can see here 6 characters, and in here you can see the number of comparisons that showed significant differences in between Naja naja and Naja kautia. Is widest part distance was the character that showed highest number of significant differences among scales in between these two species. You can here see the name of the scales. So, is widest part distance in 14 scale can significantly differentiate these two species. Each area of 13 scale can significantly differentiate, and other characters also you can see here 2, 4, 5, 7. All of this scale can distinguish these two species. And for here you can see we have compared between sexes of these two species, and also here we have been able to distinguish between this male and female specimens of Naja naja and Naja kautia. For Naja naja kautia, age area was the most significant. 9 scale of Naja kautia can distinguish male and female specimens. Number of follicle per 20,000 micrometer square of 5 scale can significantly differentiate between male and female specimens of Naja kautia. And here you can see for Naja naja, these two species is also applicable for Naja naja. 3 scales and 2 scales respectively distinguish between male and female specimens of this species. And here you can see that when we have used all the data, the clustering is overlapped, but when we only use the characters, those significantly differs between the two species, the clustering is completely separate from one another. That means there is no overlapping. And here you can see the male and female differentiation using principal component analysis. When we used all the data, there is overlapping in both cases. But when we used only the significant data that significantly differs between male and female of Naja naja and Naja kauthia. Here you can see clustering for Naja kauthia, male and female specimen, and here you can see Naja naja male and female cluster that is completely distinct from one another. Finally, our method is not a qualitative approach, but quantitative, that is highly reliable. This method can significantly differentiate between snake species, and not only species but also sex can be differentiated using this method. And if this method is used, biodiversity monitoring will be more perfect, I believe, and habitat utilization pattern of snake species will be more understandable, because we often cannot find snake when we survey in the field because of their hidey nature, and also their ecological study will be perfect, I believe. And finally, we recommend this method as time worthy, cost effective, because it do not rely on heavy instruments or chemical, something like that. And this is highly reliable because we have statistical methods, actually uh, risk-free, because it need not to handle live snake specimens, and it is also non-invasive for the snake species, because it need not to kill the snake. We deeply acknowledge our research and publication cell of University of Chittagong, Venom Research Center, and Ecoclimate Lab, Bangladesh. And that's all. Thank you for your attention. Uh, thank you.
Thank you. We're going to go ahead and move on to